We've already studied parametric equations, and this might be a good time to review them a little bit so that we can have a look at how we can actually differentiate them. Now, we've seen that we can use this format dy dx, even though it's not strictly a fraction. We can use the fact that it looks like a fraction and it behaves like a fraction in certain ways to do a few tricks. Now, the trick that we're looking at here is finding dy dx when we don't have dy dx, but we do have dy dt and dt dx. Now, notionally here, what we're looking at is the fact that the dt's will effectively cancel out and give us dy over dx. Now, how are we going to get dt dx? Well, you might notice that this is just the reciprocal of dx dt. So in other words, if we can differentiate y with respect to t, and we can differentiate x with respect to t, both of which should be fairly straightforward, then we can find the reciprocal of the second one, and we can multiply these together to find dy dx. Now, this rule is written in two different forms here. To me, this one makes the most sense because I can see the things cancelling out, but it has the slight annoyance, I suppose, that one of the parts is the reciprocal of the part that you will have found. So a lot of people prefer this format, where we basically say, look, if we want dy dx, then we can find dy dt and dx dt, and just divide this one by that one. The other way that you could write that is dy dt over dx dt, where clearly the same thing happens, the dt's cancel out. So pick your favourite, I think, here. You could write them both down if you like, but I would pick your favourite and say that's the form that makes the most sense to me. That's the one I'm going to remember and use. So let's have a look at two methods then for finding dy dx for this pair of parametric equations. Now, why on earth would we do it in two different ways? Well, it's a good way to just check your understanding of this method. So the first way we're going to do it is just by creating a Cartesian equation out of this. And that's good revision if you're kind of saying, what was a parametric equation again, and you can't quite remember. Now here we have x in terms of t, and we have y in terms of t. So if we want y in terms of x, then we just have to solve these simultaneously. So basically pretend that this is equation 1 and this is equation 2, and we want to sub one into the other. You can sub either one in as you like. I think the easiest way to do it here is probably to change the form of equation 1 so that you've got t by itself, and then sub that into equation 2. So my method would be to say, therefore, t equals x over 2, just by rearranging that first equation. Therefore, y equals, now y is equal to t squared. So if t is x over 2, then it's x over 2 all squared. And that's the same thing as, running out of space here, x squared over 4. Okay, so now I have my Cartesian equation, y is equal to x squared over 4. You might also have written that as a quarter x squared, same thing. That's quite easy to differentiate using the trick. So dy dx is equal to, well, what's the trick again? We need to take the 2 and bring it down the front, multiply it by the quarter that's already there, and that gives us a half at the front. And then reduce the 2 to a 1. So we just have x to the power of 1, or x. And you could write it that way, or you could write it as x over 2. So that's how we find dy dx here, and if we know how to convert to a Cartesian equation, then of course this method is fine. But we're trying to learn some new methods here, and perhaps with a different set of equations, this method might have seemed tricky. Perhaps when you created y equals something in terms of x, maybe it was a type of equation that you don't know how to differentiate. In that situation, you would want method 2, so it's always good to have a backup. So we're going to use this rule. I'm going to use this one because it's my favourite, but if you prefer this one, sub it straight in. Okay, so parametrically what we want then is we want dy dt. So I'm just going to go straight in with writing dy dx equals dy dt times dt dx. Alright, so dy dt equals, well, can you differentiate y with respect to t? Yes, very easily. Just bring the 2 down and you're going to have 2t. And can you find dx dt, where we have to differentiate x with respect to t? Yes, that will give us just 2. So now we have both ingredients that we need for our recipe, except for this one, of course, we'll need to take the reciprocal of because I'm wanting dt dx And I've got dx dt, so I'm going to have to flip that upside down. I'm also sort of running out of space. I might continue up here. Normally I just continue working down. So dy dx is equal to 2t multiplied by the reciprocal of 2, which is a half. And when I do that, I've just got t. Okay, now it feels like we're finished here, but we're not. Why aren't we? Well, because we're finding dy dx, and our answer is t. That doesn't really make sense, does it? If you're differentiating y with respect to x, you expect an answer that's got x's in it. So at this point, you need to be careful not to stop, but to keep going. So what's t? Well, here we've already thought about that. But if you hadn't, if you've just been sticking with this method, you'd need to use one of these, you'd need to use this equation to get t by itself. So I'd probably set it out by saying, and t is equal to x over 2, therefore dy dx is equal to x over 2. Because if it equals t, and t is this, then it's actually this. So your solution must be in terms of x. So write that down as a note to self, to not finish until you've converted your t's back into x's. Must be in terms of x. Okay, so we've got the same method there as where we did it this way. If you're thinking for a question like this, that this is your preferred method, then you can use it. If it gets you the right answer, you're good to go. But knowing this other method could be really important if once you've made your Cartesian equation, you get something in terms of x that you actually just don't have the skills to differentiate. And this could turn out to be much, much simpler.